Okay, so today's video is focusing on key features of radical graphs. And we have two different radical graphs that we're going to look at. The first is a square root graph. And then the second is a cube root graph. So we're going to start looking at the parent functions of these graphs first, and then we'll go into looking at some of their key features and applying some of the transformations that we've learned about this year. So before I do anything else, I need to know what this graph looks like. So I'm going to come over to Desmos, and I encourage you to do the same so that you know how to graph this. I'm going to square root and x. Okay, and I see my purple graph here. So it looks like I have a special point, a starting point or an ending point, whatever way you want to look at it, at 0, 0. So I'm going to go ahead and sketch that here as well. So I put a starting point at 0, 0. It just kind of comes up and curves to the side. So there's a sketch of my parent function. And I can always use Desmos to tell me about some of the points that are on my parent function. So I'm going to open back up the window. I'm going to look at this little settings button, hit the settings gear. And then here there's a table button. So I hit the table button and it tells me about some different points that I have. And as it puts them in the table, it also shows me where they are on the graph. So obviously, these points where it says -2, if I went over to -2 on the x-axis, I would see there's no part of this graph at -2. That's why it says undefined. Same with -1, and it's not until 0 that I'm actually getting an x value that works. So in my table, I'm going to start it at 0, 0, because that's the first point that works for me. The first point that shows up in this function. The second point I see is the point 1, 1. Okay, and then I don't really need to deal with that long decimal because there's an infinite number of points on here. So I'm going to click into the 2 row and I'm going to try 3. Does 3 give me a nice number? Nope. But 4 does, right? So it says 4 and 2 would be my next point. And hopefully you're seeing a pattern here that all of the points that give us nice numbers are perfect squares, since we're taking the square root of that x value. So here, the next perfect square that I could come across is 9. So I'm going to put a 9 as my next one. And I get 3. So the next point would be 9 and then 3. So you're not always going to have to find points, but just wanted to remind you that you could find points if you needed them. But now we're just going to go back to looking at our picture. So remember that domain are all of the possible x values for our graph. And I'm using this in so I can write a little bigger. And range is all the possible y values. So if I want to list all of the possible x values, our table helps us see that we didn't have any x values that were less than 0, right? 0 was the first x value that works in our function because we can't take the square root of a negative number without making it imaginary, and we can't graph imaginary numbers. So our domain for this one is going to be from 0, because that's where our possible x values start, and it goes to the right forever and ever. So since it goes to the right forever and ever, I'm going to say it's from 0 to infinity. Okay? And we're looking right to left for x values. And then for our range, we're looking at our y values. So we're looking up and down. So if I look here at my graph, I can click on this point, I see that the lowest y value is also at 0. So this range is going to start at 0. And even if I were to zoom out on this, I kind of never get to see how high or how tall my graph goes. It's not getting a ton bigger, but it's getting a little bit bigger even as I zoom out. So that means that it's going up in the y direction forever and ever, which means it's going to go from 0 to infinity. Now, when it comes to the x-intercept and the y-intercept, our radical functions aren't always going to have an x-intercept and a y-intercept, but we can always look for them by looking for places where they cross or touch the x or y axis. So in this case, I only see one place where it crosses or touches, and it actually crosses or touches both of them. So one point would be our x-intercept of 0, 0, and then our y-intercept of 0, 0. And our square root function graphs don't have to have an x-intercept or the y-intercept depending on how they're transformed. Okay, some do and some don't, and we'll see that a little bit later in our notes. Okay, so let's take a look at our cube root function. So I'm going to change colors for this one. Maybe this one I'll do in red. And I'm going to go back to my graph over here. I don't need my square root anymore. And I'm going to do the cube root. So I need that little 3 on the outside. Depending on which version of the Desmos calculator you're using, it might not pop up in this little short window. So you can just go over to Functions and then scroll down to the bottom where it says Number Theory, and then you're going to click this button right here because I want a 3 on the outside and then an X on the inside. So this one gives us a fun little S shape, right? It looks like we have a turning point at 0, 0, but then it kind of curves up to the right and down to the left. So I'm going to try and make my best drawing of that on my picture. So I have that turning point at 0, 0, then it goes up and to the right and down and to the left. Remember, these are just sketches, so we're going for the overall shape, but it doesn't have to be a perfect drawing. And then just like we did with the cube root function, or the square root function, we can do with the cube root function. So we can go to that settings gear and then click the table to see where we have some points. And this is definitely different than our square root function because we can have negative x values, it looks like. So I'm going to start with -1, -1, because that's a nice point that I can put on my table. And then after -1, -1, I say I have the point 0, 0. And then the point 1, 1. Then I want to find one more. So if I go to my table, if I put 3, 3 doesn't give me any nice numbers. 4, these are all still points, but just not ones that we need to be familiar with. 6, no. 7, no. But 8 works because 8 is a perfect cube, right? 2 times 2 times 2. So 2 times itself 3 different times is going to be 8. So we have an x of 8. We have a y of 2. So going back to look at our domain and range, I just need my picture again. And domain is talking about x values, the possible x values for this function. And when we looked at that table and looking at our graph, we see that we have lots of x values that are negative that work for this cubed function. So our domain here goes all the way to the left, which is negative infinity. But our domain is also going all the way to the right, which would be positive infinity. So another way that we can label a domain like this is it's all real numbers. But we want to practice looking at it as infinities too, because I think all real numbers is a little bit easier to understand, but often not how they write it on the EOC. Next, let's look at the range. So the range is talking about all of the possible y values. So if we're looking kind of like down, right, we want to look for the lowest possible y value. I'm going to keep zooming out my graph here. And it seems like if I look at this left end, that it just continues to get a little bit smaller no matter how far I zoom out. So that means it's going down for forever, as long as I can tell. So my range is going to be from negative infinity. And then I need to know the highest point, or the biggest y value. So again, I'm going to keep zooming out. Going to see, and it's still getting just a little bit bigger every time on that right side. So it's going to be from negative infinity to infinity. Again, these graphs, most of the time are going to have an x-intercept or the y-intercept, but we are just going to look for, where they cross the x-axis or the y-axis. So here, see that I have just really one special place where it crosses for both the x and the y. So both the x-axis and the y-axis, or intercept, are going to be 0, 0. Perfect. Okay. So now we have some information about our parent functions, just kind of familiarizing ourselves with what they look like, and then maybe starting to think about how we can move them around. So our first example says sketch a graph and identify the key features for each graph. Okay, so let's go ahead and type in this square root graph here. I'm going to leave the other one up there just so whenever I go to graph a cube root, it's there. Type y equals square root of x plus 4 and then plus 3. You really want to make sure that when you have a number that's added or subtracted on the outside, that you're making sure it's on the outside of the square root when you actually type it into Desmos. Because if I put that 3 inside, it would give us a different picture. So I see here that my ending point has moved a little bit. I see like kind of have an ending point there, and it's at like negative 4, 3 if I look at it. So when I draw my picture, I want to make sure to put it at like negative 4, 3, somewhere in that quadrant. And then draw it that way. Because it still hasn't changed the way it's like rotated. And we can even label that point on here. Negative 4, 3. If it was hard to see that point, you can always go to your settings, gear, and it'll give you a table. It's always going to give you the ones that are closest, like negative 2, negative 1, 0, 1, and 2. But I could just type in, okay, I think it's at negative 4, but I want to check. So I type in negative 4, and sure enough, it gives me 3. So now we want to state the domain and the range. So for the domain of this function, we're looking at x values. Domain is always x values. So here, I see that the smallest x value that I have is a negative 4. So my domain starts at negative 4. Okay? And then when I look for the biggest x value, I could zoom out all I wanted to on this picture, and it would never change that there's not an end on the left side. So my domain is going to be on the right side. So my domain is going to be from negative 4 to positive infinity, because it goes on and on to the right forever and ever. Now I'm going to look at the range. So I'm going to look at the up and down portion. So when I look for the lowest y value, or the smallest y value, I see that that's kind of at 3, right? That's the lowest point on my graph. So my range starts at 3. And even if I zoom out, I see that it's like continuing to go up just a little bit, but it's still going up. So my range is going to be from 3 to infinity. And then here, it's only asking for the y-intercept. So I want to look for where it crosses the y-axis. And Desmos gives us a nice little point for that. So my y-intercept is going to be at 0, 5. So just to kind of help us connect the dots here, I'm going to put a basic parent function on our graph so we can see how it transformed. So if you think back to transformations, before we learned that anything that's like inside the parentheses, or in this case, under the radical, is going to move it left or right.
Or a wrestling sponsor to reach out or come to the main office. And we have a wrestling coach to call or come up to the main office.
So this here, this x plus 4, is going to move it left 4. And we can double check that here. If we started at the blue and moved to the purple, we would have to go to the left 4. And then this plus 3 on the outside is going to move it up 3. So we can check that again. If we started at the blue and moved to the purple, we would have to go up. So that's kind of what it looks like to sketch and then identify key features for a square root. So we're going to do the same thing for part B. If you want to try this on your own, you can pause the video at this point, try to do it on your own, and then jump back on in a minute to see if you did it right. If not, you can just continue to follow along. But I'm going to leave my parent function on there, just not show it, and then I'm just going to put my new numbers in here for this one. So now I have my new picture, and whoa, let's put my parent function back on there. The purple one looks pretty different from the blue one this time. So it looks like I have an ending point at 1, 0. So make sure to put that on here. And then it actually goes down in the opposite direction. So if we want to talk about the domain here, even though it looks different, we're still looking at x values. So the smallest x value that we see here is 1. And again, even though the picture looks different, if I'm looking for the biggest x value, I'm going to look as far right as I can on my graph. And I don't see an end when I go to the far right. It just keeps going. So since it keeps going, we're going to say from 1 to infinity for our domain. And then our range gets a little different this time because our y values are in the total opposite direction. So for the range, if I'm looking for the lowest y value, even if I zoom out, there's like not an end to the lowest y value. As I keep zooming out, it keeps getting lower and lower and lower on that purple graph. So my range starts at negative infinity because it's going down forever and ever. And then the biggest y value is actually right here on the y-axis because my purple line doesn't go above the y-axis. So my range would go from negative infinity to 0. And here, I want to look for the x-intercept. So it's just the places where it crosses the x-axis. So here it crosses at the point 1, 0. And I see that this doesn't have a y-axis or a y-intercept at all. It never crosses our y-axis. So that's how we look at two square root graphs. And actually, let's talk about identifying the transformations. I almost moved on without doing that. So we know that this negative that's in front is going to reflect over the x-axis. That's why instead of going up and over, it goes kind of down and under. And then this 2 is going to give us a vertical stretch. So if we look at the purple one compared to the blue one, the purple one definitely kind of arcs out more, especially in the beginning. It kind of stretches out, looks a little bit bigger. And then here, that's going to move it right 1. Perfect. So let's look at how this could look with a cube root function. So good thing I kept that cube root in there, right? Makes it a little bit easier. So I'm going to go ahead and leave my parent function up there. That's the purple. And then go back to functions. Do my specific one here. Oops, that's not what I wanted. There we go. So put that 3 on the outside. And then I have x plus 2 on the inside. And minus 1 after that. So the green one is my new one. So just so we can get a picture drawing here, I'm going to zoom in. And it looks like we have kind of a new turning point right here at -2, -1. So in my picture on my paper, I want to make sure to reflect that. It's like my turning point right there. I know it's going to go up this way and down that way. So again, if we're looking for the domain, we're looking for the x's. So I'm going to zoom out and see if there's anywhere where my x's like start and stop in either direction. And even if I look far to the right or far to the left, that doesn't change. So my domain is going to go from -infinity to infinity. And then same with my range. My range never stops from the lowest y to the biggest y. It just keeps going. So my range is -infinity to infinity. And this is actually always going to be the case for cube root functions. So that makes it nice and easy to find the domain and range if you can remember that they're both all real numbers. So now we're just looking for the x-intercept and the y-intercept. So if I click right there at that dot, it shows us we have an x-intercept of -1, 0. And we have a y-intercept of 0, 0.26. So we can have decimal points or fractions for our x and y intercepts. That's totally fine. A lot of the examples we do work out with nice even numbers just because it makes our life easier, but that doesn't mean that they're necessarily going to be that way on the EOC. So if Desmos says there's a point there, you can trust that there's a point there. And then let's think back to those transformations and see if that matches up if we were moving from the purple graph to the green graph. So we here have +2. That's like under our radical or inside like we talked about. So that means that this one would move left 2 units, which is definitely true here. To go from purple to green, we'd have to move to the left. And then -1, just going to be down 1. And again, that's true. If we wanted to move from purple to green, we would have to pick it up and move it down. So that's our first cube root function. Now let's look at our second one where we have a little bit more going on. I'm going to go ahead and update my equation here. We'll see it kind of switch every time. There we go. So this is definitely interesting when we look at just our green one to draw a picture. When we reflect over the x-axis, it kind of just changes the way the s goes. Instead of starting low and going high, starting high and going low. It looks like we have a turning point at 0, 2. So I'm going to go ahead and draw my picture. For some reason, it's harder for me to draw this way, but we'll make do. Looks kind of something like that. And if you were paying attention in the last example, we learned that the domain and range for all cube root functions is always the same. So from negative infinity to infinity and negative infinity to infinity are all real numbers. To find our x-intercept, we're going to have to zoom out a lot, but we can click on our graph and we can see that we have a point at 64, 0. That's our x-intercept. And our y-intercept is a little bit easier to see. It's at 0, 2. So again, if we wanted to talk about our transformations really quick, I'm going to put our parent function back up here. Try to get us a little back in order. So there's our parent function. So we're going from purple to green. So we go from purple to green. We know that this minus is going to reflect it. And then this 1/2 is going to compress it. So you'll see that the shape of the purple and green look a little bit different. We zoom out. The purple is like a little more stretched out. It's what we call compression. Both a stretch and a compression just kind of distort the way it looks. So you can't always tell just by looking at it, but the numbers can help us see. And then this +2 is going to move it up 2. And to go from purple to green, we would definitely have to pick up and move our function up 2. So if you don't remember transformations super duper well from before the break, that's okay. Maybe you've just been kind of like, wrong one, muddling along with this. But now we're going to actually define what those transformations are going to look like. Okay, so a horizontal translation is inside whatever's going on. So I'm going to show you like what it looks like for a square root, but we can apply all of the same things to cube roots. Yeah, so they can all be like that, but I'm just going to use square roots in this table. So if I have square root of x minus 2, that would be moving it to the right 2. If I had square root of x plus 5, that would move it left 5. And then anything outside is going to be a vertical translation. So I have a square root of x plus 6. It's going to move it up 6. And square root of x minus 3. It's going to move it down 3. And then a reflection. So we put the negative out in front. It's still going to reflect over the x-axis. So flip it upside down. And then vertical stretch and compression. So that's when we're multiplying by a number on the outside. So if I have 2 square root x, that's a stretch by 2. If I have 1/3 x, that's a compression by 1/3. Okay. So our second example tells us, without graphing, identify the following transformations. So for each different thing, in addition to a square root or a cube root, we should be able to find a transformation. So here, I see a minus sign in front. That means it's going to reflect over the x-axis. I see this +1 in the middle. If I go back and look at my table, that tells me it's going to go left 1 unit. And then this -4 at the end is going to go down 4 units. So I kind of had 3 additions to the x squared function. So that means that I needed to have 3 transformations listed. Part B is a cube root function. So that 3 isn't a transformation. The first transformation I see is this 4. And if I look at my notes or my table, I see that that's going to be a stretch by 4. And then I also see this plus 5, which means I'm going to go left 5. If you were on a test or a quiz and you weren't sure, you could always graph them. Even now, you could pull up Desmos and graph them. But it can save you time if you're able to look at the equation and know what the transformation is without having to graph. But then in part C here, again, I see 3 different things happening. I see this negative in front, so that's going to be my reflect over the x-axis. And then I have my 1/2. So that's going to be, if I look at my notes, it's a fraction. So that's going to be the compression by 1/2. And then that plus 2 at the end is going to move me up 2 units. And you could graph all of those to double check, but like I said, it's a time saver if we don't have to graph them. So that is the end of our transformation and key features of radicals notes. Make sure to look at that, next lesson, that slip on top of your notes paper to see what other activity you need to do today to practice. But this video will be posted for the rest of the year in case you need to refer back to it.